Welcome to the NMENA video tutorial Unit 4.9 Measurement of Mechanical Properties of Parabolic Trough Collectors. My name is Christoph Prahl. I've been working for 5 years at DLR in the CSP fields optical measurement of concentrator shape and collector development. Let's have a look on the content of this unit. We want to know why it is important to measure the mechanical properties of CSP collectors. We will have 2 examples of use. One is the parabolic trough torsion stiffness, and the second one is the stiffness of the absorber tube support of a parabolic trough, in particular its lateral stiffness. We will present the measurement setup and the required instruments, and we will see an example of evaluation. So why is it important to know the mechanical properties of CSP collectors? We have very high demands on shape accuracy to achieve the aimed at optical performance. In addition to the high demands on the shape accuracy, this shape must be maintained under operating conditions. So if there is wind load or static unbalance, wind load and friction of the bearings, all these forces try to deform our collector. So the stiffer it is, the better is the shape accuracy under operating conditions. We have here a rather complicated example to visualize the influence of parabolic trough stiffness on its optical performance. On the right vertical axis, we see the wind speed. In general, wind speed has an influence on the shape of the collector because the wind force induces a torque, and the torque is followed by a torsionousness of the collector. We have the blue and the orange line showing the average twist of the collector, and this twist is increasing with increasing wind speed. The higher the twist is, the higher is the spillage, which is the amount of radiation lost which not hits the absorber tube. We can now check for a certain wind speed and get the twist of the collector, and from the twist we can determine the amount of spillage. So what we see here is the higher the torsional stiffness, the lower is the twist and the less spillage we have, so we have better optical performance. In this particular case we have a comparison of 2 collectors. Orange is the Eurotrough and blue is a former R3 collector, and the optical performance has been improved by improving the torsion stiffness. Another important feature is the lateral stiffness of the absorber tube support. So in general, the absorber tube is quite heavy, so its dead load tries to pull away the absorber tube from its design position depending on the elevation angle of the parabolic trough. We see here a graphic. On the left, we have a parabolic trough collector in horizon position, so the gravitation force is pulling the absorber tube towards the ground. In zenith position, there is no lateral force, but due to the force we assume a lateral deviation which is depending on the elevation angle of the parabolic trough. To estimate the influence of the deviation of the absorber tube from the focal line, we have a graph which shows the height and lateral deviation of the absorber tube from its design position and the influence on the optical performance. We see here the measurement equipment which is required to measure the torsion stiffness of the parabolic trough. This consists mainly of 2 digital water levels and clamps to fix them to the structure, and we have wedge lashings and a force meter to apply and measure the torsion. The setup of a torsion measurement is as follows. We put one of the inclinometers, or also called digital water level, to the rear end plate of the collector, and we put a second inclinometer to the front end plate of the collector where the drive pylon is located. Then we apply a torque with the wedge lashings and the force meter to the rear end plate. On the other side, the hydraulic stamps of the drive pylon fix the collector. So a rather small rotation around the axis of rotation is possible here, caused by the applied torque. If we increase the torque, we will measure a small torsion which corresponds to the angle difference shown by the inclinometers. And from the slope of that particular line, we can calculate the torsion stiffness in units kilonewton meter per milliradian. We will now have a look at the measurement setup to measure the lateral receiver support stiffness. In this graph, we see a parabolic trough, a cross-section, and we have the distance of the absorber tube center from the mirror edge, denoted by x. If we now apply a force F to that tube, there might be changes in this distance x, which depend on the stiffness of the support. We can increase the force F during the measurement to a maximum value of 500 Newton, which corresponds approximately to the gravitation force of a single tube. We then measure the variation of the distance x between absorber tube and outer mirror edge depending on the force. For the evaluation, of a lateral receiver support stiffness measurement, we can plot the lateral position of the receiver versus the applied force. In this particular case, for the yellow line, we see that with increasing force, the lateral position is changing, and if we release the force, the deviation is smaller than with force. But in this particular case, we see that the position before and after the measurement is not the same. So the applied force has introduced a plastic deformation of the receiver tube, which is not allowed in operating conditions. So in this particular case, an enforcement of the receiver support is necessary.